back to my channel and let us continue the recurrence relations using linear algebra. This is part 2 of the video. If you haven't watched part 1, please, I request you from the I tab, you can check out the part 1 first and then come back to this video. Okay, so in part 1, we formed the equation. Okay, let us call this next term as un, okay, because it is finding the nth term, okay, of the recurrence relation. Okay, and this was the matrix A or the bases and the inputs or the smaller problems. Okay, so next let us move on to the concept of eigenvalues and eigenvectors that will be useful to form the characteristic equation and finding the eigenvalue. If you don't know what eigenvalue and eigenvector is, don't worry. I will give you a short intuition in easy language. What does it mean? Eigenvalue and eigenvector. Okay. All right. So first I will tell you what an eigenvector is. Okay. So the matrix A that we wrote or any matrix transformation matrix A, uh, when any a vector x when transformed using matrix A, it results in only a scalar value stretch or a squish in the direction of the same vector is known as an eigenvector. These are special vectors where the matrix A, same transformation matrix A, like suppose x was in this direction, okay, after transforming the matrix A, suppose doing rotation or reflection, the same transformation is nothing but this vector's direction does not change, only a scalar is multiplied. So if originally the vector was this, the vector in the same direction, only the magnitude would same, but the direction would be, only the magnitude will be different, but the direction would be same. These are special type of vectors. Okay, so it makes the transformation A, when you apply this transformation multiple times on input vectors, or we can say the power A ki power kx है ना, this is the benefit. Suppose this was k, you are repeatedly applying the same transformation on this vector a a a not only this vector, any vector. Okay, but if you are in the eigen coordinate system or the coordinate system where your bases, independent bases, are the eigen vectors, okay, x1, x2, these are the eigen vectors, then the resultant transformation is nothing but a scalar multiplication. Means either you will stretch this vector eigenvectors or squish this eigenvectors with. Otherwise, in the original coordinate system, I cap and j cap, you have to do so many matrix multiplications. Okay, that is the benefit in eigen coordinate system, where the eigenvectors are the basis of that coordinate system. The repeated transformation are nothing but lambda power k, means how many times you are multiplying, pre-multiplying, the doing the transformation A, that would be nothing but lambda that many times. So here 3 times we have done, so lambda 3 times. Let us write this vector A, nothing but in eigen coordinate system lambda cube times that vector A in eigen coordinate system. Eigen coordinate system. That means you don't have to do that many times of matrix multiplication. That saves time, okay, and gives you results faster. That is the benefit of eigen coordinate system. So let us understand, okay, let us erase this. Okay, so I told you the vectors which are of this form ax is equal to just a scalar times the vector x. So from here, now I will telling you about the characteristic equation. Characteristic equation. Okay. So what is the characteristic equation? Now, if I bring all the vectors on one side, this is a matrix, this is a vector, this is a scalar, this is a vector. Now, we used to solve the equations ax equals to b, right? Finding the independent bases, the dependent bases, and we used to find using elimination the vector x, right? But here we cannot do that. We cannot use elimination over here. That would change the value of the scalar lambda. We don't want that. Okay. So what we will do is and we know that for finding solutions of ax equals to b, A has to be a square matrix. So here also A needs to be a square matrix so that we will have a null space and a vector space. Okay. I will explain you in short what null space is. Just wait for a moment. So A, we will bring this vector, this is also a vector, on one side of the equation. A minus lambda times I x is equal to 0. Okay. So we know that, okay, now I will tell you about what null space is. Okay. So we need the values of lambda such that this transformation, this is a transformation matrix, right? A minus lambda I is nothing but a transformation matrix, right? Times x is equals to 0. One solution to this equation is when x is 0, right? When x is 0, 0, 0, this is a solution to this equation. Because 0, 0, 0 when transformed with any matrix or this matrix's bases stretched by 0 units results in 0. After transformation, it becomes 0. Okay. So that we don't want because we want to make the eigen, we want such lambdas, right? Such that this eigen vector corresponding to it should be non-zero, or the null space should be non-zero, non-trivial, right? What is null space? In the input coordinate system, those vectors, suppose this blue line, these vectors after doing a transformation, if you give input these blue a vectors after transformation, they are mapped to 0. Okay. This is after transformation, the coordinate system after transformation. Okay, this blue line after transformation, they are mapped to the 0. Okay, so you cannot get back which original vector was the input. Means you can go from this blue line to this null space, but if you want the reverse of it, A inverse, you cannot get back all the individual vectors which were mapped to 0. Okay, so this is the null space of A. Null space of A means from the input coordinate system vectors, which vectors after transformation by A matrix becomes 0 vector. Okay. So we want non-zero vectors which after transformation with A minus lambda I becomes 0. Okay. So how do we do that? Okay. I know that, we know that, right? This x vector is not 0. Then this A minus lambda I, the determinant of it has to be 0. That is, it has to be singular. What does singular means? Okay. I will give you a short, quick intuition. Okay. So, A minus lambda I, the basis of it, suppose the number of columns or the independent basis it should have is 3. But we found out that the the third vector is not adding any new information in the that direction is not adding any new information. It's a linear combination of first two. That means it is lying in the plane, on the plane. Okay, let us make it a little differently. This is not a very good way of to draw it. Let us make a cube, okay? That would be better. Suppose your input coordinate system, let us draw it like a cube. Okay. Okay, right. Because it's a 3D, that's why it's harder to represent on a 2D screen, but I will try my best to show it on a 2D screen. Okay, suppose this is your X, this is your third coordinate, and this is your Y. This is the original coordinate system. All the vectors inside this cube are input. Okay? And then suppose after transformation with A matrix, okay, the A matrix's columns represent, right? The A matrices columns, they are not all independent. The first two are perpendicular to each other or independent. Okay, they are adding new information in new directions. But say the third basis of the third column of A matrix is not adding any new direction. It is simply lying on the plane of the first two like this. Okay, now I hope you are able to see. So this portion is lying on the same plane, same face, right? This portion, okay. This portion is lying on the same plane as x, y. It is lying on the xy plane, this third basis. It is not adding any new information, new direction of information. It is simply the can be derived from x and y, okay. So what will happen? You cannot in the input coordinate system, the z, okay, the z information, this direction's information will be removed and will be mapped with 0, right? Or lying on the plane. Okay, some information is being removed. So these vectors in the input along this z direction, they are mapped to 0. Okay, so this was the concept of null. This vector will be, these vectors in the z direction will be your null space, right? Null space of vector a minus lambda I, right? So I hope you understood this. Huh, oh, okay, okay, sorry. I was telling you about what is the meaning of what we will do, right? So now we know this green portion, this XY plane. What is the volume of this XY plane? Okay, this is just a plain sheet of paper. If I draw this green part like this is a green sheet of paper and it is not having a height. So what will be the volume of this? This will be having an area, but the volume would be 0, right? So what we will do is, I know that as the dimension or the independent information the basis we're adding is less. It cannot represent the entire input, all the vectors. So the volume of the parallelepiped from this matrix would be 0, or the determinant a minus lambda I would be equal to 0. Okay, from here we will get the characteristic equation or the equation that will give us the value of lambdas. Okay, such that from the lambdas, values of the lambdas, we will plug in the value of lambda over here in this equation and solve for x. Okay, to get for every value of lambda, we will get a unique value of the eigenvector. And these eigenvectors x1, x2, x3 we will make them the basis, the independent basis for our new eigen coordinate system like this. Okay, and then again I will explain how they are useful in solving further steps for solving the recurrence relation. Okay, so for the previous question, the question in the previous slide, let us calculate the characteristic equation and then we will move on to the next step. Okay. Okay. So this was the question. This was the matrix A. 3, 1, minus 2, 0. Right? We will write it over here. A is 3, 1, wait. 3, 1, 3 minus 2, 1, 0. 3 minus 2 minus 2, 1 and 0. Now let us find determinant of A minus lambda I. So that would be 3 minus lambda minus 2, 1, 0. I think you can write this still here on your own. You can think about it because I is nothing but the identity matrix where diagonals would be 1 and remaining things would be 0. And if you multiply by scalar lambda, it will become like this. And you subtract with A minus lambda I, we will get this. Now we will find the determinant that is equal to 0. That will be equal to 0. So that would be 3 minus lambda times 0 minus, oh sorry, it won't be 0, it is minus lambda, right? We are subtracting lambda. So that would be 3 minus lambda times minus lambda, this into this, minus this into this, minus 2, right? So that would be equal to 0, or this will be minus lambda into minus lambda, lambda square, minus 3 lambda, then plus 2 is equals to 0. If we solve, what we'll get? Lambda square minus 2 lambda minus lambda plus 2 is equals to 0. I will erase the upper part and continue over there. Okay, so we'll continue over here. So lambda, okay, from here we are continuing. Okay, so lambda common, lambda minus 2 minus 1 common, lambda minus 2 is equals to 0. So from here we will get lambda minus 2, lambda minus 1 is equals to 0, or lambda's value will be 2 and 1. Okay, so we will have two eigen vectors for lambda equals to 2 and lambda equals to 1. Okay, so let us calculate in the next slide what would be the eigenvectors. For first we will find for lambda is equals to 2. Okay, we will plug in A minus lambda I, the value of 2. So we will have 3 minus 2, right? And then minus 2, right? Minus 2, then 1 and minus 2, right? Yeah, and times x1, okay, let us write the eigenvectors as v. Okay, v1, v2 is equal to 0, right? So we will get this 1 minus 2, 1 minus 2, and v1, v2 is equals to 0. So what should we plug in v1 and v2 scalars to get to make this vector as 0? I know that v1 is multiplied with the first column and v2 will be multiplied by the second column. So if we plug in v1 as 2 and v2 as 1, then this will become 0. So that means our eigenvector v1 is nothing but, okay, let us use a different notation, x1. x1 eigenvector is 2, 1. 2, 1. Okay. So we got our, for lambda 1, we have got our eigenvector. In the next page for lambda 2 is equals to 1, we will again solve it. So a minus lambda I, put the value of lambda over here. 3 minus 1 minus 2, 1 and minus 1 times, this time we will write v3 v4 is equals to 0. So we'll get 3 minus 1, 2, minus 2, 1, minus 1. So what should we plug in V3 and V4 to get 0, 0? I know that V3 is scalar multiplied on the first column and V4 is the scalar multiplied on the second column. So we should multiply V3 with plus 1. So V3 should be plus 1 and V4 should be 1. So that means, right, 1 and 1, that will make it 0. So our x2 would be 1, 1. So we have got our both eigen, for both eigenvalues, we have got our both eigenvectors. Okay. Now what we will do is, we will, in the next part of the video, we will try to understand the eigen coordinate system, what is the value of S, what it means, the intuition or the in real world what S means, what S inverse means, what S inverse lambda S it does, and how we can use it to solve the recurrence relations that we discussed in the part 1. So hope you enjoyed this video. Please share it with your friends, subscribe to my channel and stay tuned for more intuitive mathematics videos. Till then, happy learning and just be better than you were yesterday. Thank you and bye-bye.